Hi everyone, my name is Malini Thomas and I'm going to explain few basics in trigonometry. So trig means triangle and metry means measurement. So trigonometry means measurement in triangles. And what exactly these measurements in triangles? Yeah, it could be the sides or angles of a triangle. And trigonometry is that branch of mathematics that deals with this relationship between angles and sides of a triangle. But angles and sides, both different. So how can we equate? The angles are measured in degrees of radians and sides are lengths, which have integer values. So how do we connect? There must be some functions that can equate these two. And these are nothing but trigonometric functions. So before I explain what trigonometric functions are, I'm going to take your attention to these two triangles. What can you observe? Yeah, both are right angle triangles. That means they have a 90-degree. So the two sides, the base and the height, they meet at 90 degrees, just like the walls of a room. And what about the other angle? The acute angle. Acute angle means the any angle less than 90 degree. Yeah, it is 53 for both. So when there are two angles common for both the triangles, I mean, when there are two angles congruent to each other, so both the triangles, they're similar. I think you must have studied this earlier. So what is similarity of two triangles? Yeah, they look same. The shape looks same even though the size is different. And it means one triangle is proportionally bigger or the other one is proportionally smaller. And what that means, proportionality. See, look at the sides. Look at the hypotenuse. Hypotenuse is the largest, I mean the longest side opposite to the 90-degree. And here 5 and 10, they are the hypotenuse. So when we are comparing the bigger to the smaller, the ratio of A dash C dash by AC, it is 10 by 5, which is 2. Now let's look at the other matching sides, AB and A dash B dash, 3 and 6. Yeah, just take the ratio, it is 2. And what about the heights, 4 and 8? Again, the same ratio. So we just observe that even though the size is different, the shape is same because the angles are same, they look same, they're similar, and even though the sides they're different, they're proportionally same. That means the ratio is seen to be a constant. Yeah, so such an observation we have got. And this ratio of sides, it has something to do with this angle, I believe. Yeah, let's keep that doubt. So for any right angle triangle similar to this smaller one, the ratio of the matching sides will be the same. That's what we found out. Now, let's try to label a triangle. I mean, the ratio of the sides, it has got to do something with this angle. So from the angle perspective, let's label the sides other than hypotenuse. So when I'm standing at this angle C, when I'm looking at AB, it's my opposite side. From this perspective, it's my opposite side. And BC, it's closer to this angle. So it's my adjacent side and AB is my opposite side. So when I'm looking at when I'm looking from angle A, from that perspective, it changes. BC is my opposite side and AB is my adjacent side. So from angle perspective, we now know to label the two sides of a right angle triangle other than the hypotenuse. Yeah. So we know to label and let's look at this. Yes. Here a triangle ABC. Here the sides are given and the angle, the acute angle is 30 degree. Yeah, the other angle is 90 degree, of course, in a right angle triangle. And we know the angle opposite to 30 degree, it's the opposite side. And BC is our adjacent side. And the AC is our hypotenuse. So I just want to take the ratios of opposite side to hypotenuse, adjacent side to hypotenuse, and opposite side to adjacent side. So I have found the ratios. It's 0.5, 0.87, and 0.58. Now, what I'm going to do is I'm not changing the angles. I'm keeping 30° a constant. And I'm just changing the size of this triangle by dragging the vertex C or B. Yeah, I'm going to drag these vertices. I'm going to make this big or small. The sides are changing. We can see the sides are changing, but look at the ratio. It's not changing. It's a constant. So when the angle is a constant, the ratio of the sides, that remains a constant. So again, our doubt is becoming more stronger. There has some relationship between the angle and the ratio of the sides. Let's check that. There are three triangles which looks the same even though the size is different. So look at the angles. They are right angle triangles, so 90° common for both, common for the three, and there is a 30° which is common for the three. The angles are same, they are similar, so the sides must be proportional. Means even though the sides are different, the ratio must be same. So first we can calculate the opposite side by hypotenuse. I mean from this 30° angle perspective, my opposite sides are BC, QR, and YZ, and my hypotenuse is AC, PR, and XZ. So I'm finding the ratio of opposite to hypotenuse, which I got as 0.5 for the three triangles because they're similar and they hold some proportionality for the sides. So the ratio is constant for this 30° angle. Now I'm going to change the angle. I'm going to look whether there is any change in this ratio. Yes. For 30°, the ratio was 0.5 for three triangles, and now it's changing. Yes. So for the change in angle, the ratio is also changing, but equally for the three triangles. Now what about adjacent side by hypotenuse? I'm taking the ratio of adjacent side. Here my adjacent sides are AB, PQ, and XY because they are the sides closer to my angle 43°. And I got some ratios which is a constant for three triangles. But when I change the angle, the ratio changes. And let's look at the ratio of opposite side by adjacent side. Again, this holds true. The ratios are changing, but only for a change in angle. So what can we say? The ratio changes only on changing the angle. So the ratio of the sides is dependent only on the angle. So this is what is called the trigonometric ratio. Now, we want to find more clarity in this. We want to equate that angle and the ratio of the sides with respect to that angle. So this is what? The ratio of the opposite side and hypotenuse that can be connected to the angle A. I mean, we are looking from angle A and labeling opposite and hypotenuse. So our opposite side is small a and hypotenuse is small c. So we are finding this ratio, and that value is equal to the sine of angle A. And the ratio of adjacent side of angle A and hypotenuse, that value is the same as cosine of angle A. And similarly, tan A is the ratio of opposite side of angle A and adjacent side of angle A. These ratios connect to the angles by these functions, sine A, cos A, and tan A. They have values. I mean, if angle A is 30°, sine 30, it has a value which is 0.5 or 1/2. We can read these values of sine 30, cos 45, or whatever it may be from the trigonometric tables or by using our calculators. So if we just know the measure of angle A, we can find the ratios. We just have to find sine A, cos A, and tan A in order to get these ratios. And these functions, sine A, cos A, tan A, these functions transforms the angle into this value, that value which equals the ratio of the respective sides. So these three acronyms you can use to remember the relationship. So, ca, and toa. So is sine equals opposite side by hypotenuse. And in ka, you can see the relationship cos A equal to adjacent side by hypotenuse. And toa explains tan theta equals opposite side by adjacent side. So if we have a tower and we are If we are 100 meters away from it, and if we are looking at the height of the tower but at an angle called the angle of elevation, if we know the angle and the distance between us and the tower, we can find the height of the tower using these trigonometric relationships. And these trigonometric relationships, they hold true for right angle triangles. We can also find the trigonometric relationship in other triangles as well using the law of cosines, but we just have to focus on these trigonometric ratios, which holds true for the right angle triangles. Thanks.